Okay, so welcome to 5.5 Logarithmic Functions. This is part 2 of the trifecta of the doorway to getting into advanced mathematics, all right? Laws of exponents, and then logarithms, and then trigonometry. If you've got that stuff down, you are ready for calculus. So today's objective will be to define and apply logarithms, and this is big and simple. So, the common logarithm of an integral power of 10 is its exponent. Now, common logarithm, integral power of 10, that sounds way more complicated than it is. Integral power of 10, that just means 10 to the power of any integer, like 10 to the negative 1, 10 to the negative 2, 10 to the 3, 10 to the 4. All right? So first, what's a common logarithm? Well, a common logarithm, we use a base 10 number system, so a common logarithm is a log base 10. All right? Of an integral power of 10, that's the log base 10 of 10 to some power that's an integer. For instance, 0 is an integer. And what is the common log of 10 to the 0? It's always its exponent. So guess what? The common log of 10 to the 0 is 0. All right. Now, notice how I said common log, but I wrote log base 10. Now, we don't typically write log base 10. We write a log base 10 as just log, and you're going to see that in a moment because we use a base 10 number system. Okay, so let's practice this with a little table. I'm going to give you a power of 10. So 10 to the 0, 10 to the 1, 10 to the 2, 10 to the 3, 10 to the 4, and so on until we get to 10 to any power, which we're going to call k. And then what is the common log? So that is that sentence above. The common log of 10 to the 0 is its exponent. That would be 0. The common log of 10 to the 1 is 1. The common log of 10 to the second is 2. The common log of 10 to the third is 3. The common log of 10 to the fourth is 4. And then if we go all the way to the common log of 10 to the k power, that must be k. And let's look at that in a little different format then, to make sure we have this down. So that implies, and notice now how I'm writing common log as just log. That is a log base 10. So the common log of 10 to the third power is 3. The common log of 10 to the fourth power is 4. The common log of 10 to the k power is k. Which leads to our definition of a logarithm. Okay? Definition of log right here. And this rule right here is going to help you solving logarithmic equations. So if I have the common log of x is a, and remember, the common log is a log base 10, so the log base 10 of x equals a, that is true if and only if. Now, we're going to go from a logarithmic equation to an exponential equation. What is my base? What is the base of a common log? It is 10. 10 to the, and you see this a on the other side? To go from a logarithmic equation to an exponential equation, all I do is take my base, 10, to this power. 10 to the a has to equal x. Okay? And we're essentially undoing each other here because logs and exponentials are inverses. They undo each other. So if I have the common log of x equals a, that is going to be true if and only if 10 to the a power equals x. Right on. This is big. So we're going to prove it too. That's how big it is. So you guys might be thinking, proof? Man, we haven't done too many proofs yet this year. I did a lot of proofs in geometry. All right. And this is kind of like the 2-column geometric proof. We're just going to take a sentence and we're going to prove it by making true statements. So the common log of x equals a if and only if 10 to the a equals x. So let's manipulate and see if we can prove this. Let's make a statement. Okay. The common log of x equals a. Wow, let's think about this. Now notice how I rewrote it. The common log of x equals a. But didn't I write that using superscript? So I need a base on both sides. And what I'm going to need to keep this true is I need common bases. And by the way, don't we use a base 10 number system? So let's think if we can use our laws of exponents right now. All right. And let's see. Remember this, b to the x equals b to the y if and only if x equals y. So let's see. Can I write this with common bases? And let's call those common bases base 10. So if the common log of x equals a, wouldn't 10 to the common log of x have to equal 10 to the a? And again, that's nothing more than b to the x equals b to the y if and only if x equals y. That has to be true. So now we go here. Well, can I simplify 10 to the log base 10 of x? Well, I said a moment ago that logarithms and exponentials undo each other. They are inverses. So, and these have the same base. This is a base 10 exponential, and your exponent is a base 10 log. They undo each other. So 10 to the log base 10 of x has to equal x. Boom, right there. All right. And what does x equal? 10 to the a power. Does that look familiar? Guess what? We're done. Quod erat demonstrandum. We have taken our original statement on the left of this if and only if, and we worked it down to our statement we have on the right of it. QED. We are done with that proof. Hey, I better give you a little time to process that. I wish you were here so you could ask me questions right now. But we will do this live during remote learning next week. Okay, so with that, what is this asking? What is this asking? Okay, well that's the common log of 6.3 or the log base 10 of 6.3. Now, this is asking me 10 to the what power is 6.3. 10 to the x is approximately 6.3. What's that x going to be? Well, I can't do this in my head. So the beauty of a question like the common log of 6.3 equals what? You just punch that out directly on your calculator. So x is going to be, all right, well, the common log of 6.3. I'm going to break out my calculator, and there's a common log button right on your calculator. And remember, that's a log base 10. Let me clear things, get this cleaned up. Here I go. And where's my common log? It's on the left, about a third of the way up. The common log of 6.3. And what does that equal? That is approximately 0.7993405,495. So how about if I round that answer to the nearest tenth and just say x would have to approximately be, there it is, 0.80. So if you get a question like this that you cannot do in your head, just punch it out on your calculator and approximate that answer. And if they do not tell you what to round to, as long as you round correctly, I rounded, it looks like I rounded actually to the nearest hundredth right there. 0.80, we have to give you full credit. Okay, now we're going to have a little fun with this little chart right here. And I gave you a copy of this chart without these cells filled in Google Classroom. So if you don't have that yet, print that out right now. And this is going to help us out a whole bunch in the very near future. So this is a chart that the first column I have a sound, like barely audible, a whisper, leaves in a breeze, soft recorded music, and so on. And then we're going to find the intensity level of that sound and the decibel level of the sound. Those are very different, but they work together. So, the intensity level of a barely audible sound is I sub 0. I sub 0. All right? Now, the intensity level of a whisper is 10 times I sub 0. 10 to the first times I sub 0. And by the way, to help you see patterns, this intensity level of a barely audible sound, remember, we're talking base 10, 10 to the first times I sub 0. Guess what? This one is 10 to the 0 times I sub 0. And we don't have that there because what's 10 to the 0? 1. But it might help you see some patterns here. Like, what's the intensity of leaves in the breeze? Well, we have 10 to the 0, I sub 0, 10 to the first, I sub 0. Doesn't it only make sense that this would be 10 to the second times I sub 0? And then, how about soft recorded music? Well, guess what? Already they break the pattern a little bit. That is going to be 10 to the fourth times I sub 0. Now, why they gave us a chart that doesn't have something that is 10 to the third I sub 0, I don't know, but I did not write this textbook. Now, let's continue. The intensity level of a two-person conversation, that is actually 10 to the 6th times I sub 0. The intensity level of a loud stereo, that is 10 to the 8th times I sub 0. The intensity level of the sound that a subway train makes, that is 10 to the 10th times I sub 0. The intensity level of a jet at takeoff, 10 to the 12th times I sub 0. And that's still not going to hurt your ears right here. But if you get to the point where a sound gives you pain in your eardrum, that is when we get to, and you're thinking 10 to the 4th, 10 to the 6th, 10 to the 8th, 10 to the 10th, 10 to the 12th. This is actually, we break the pattern again, 10 to the 13th times I sub 0. If you are hearing a sound at that intensity, you're going to have a little bit of pain in the eardrum. And if you do that too often, you could damage your hearing. When I was a young man, I used to get to go to a lot of concerts. And I remember a prof at the University of Portland, I think it was actually in a sociology class, if I remember right. That professor kept telling me that if you keep going to those concerts, Mike, and you go to those concerts without earplugs, you're going to damage your hearing. And I remember saying, oh yeah, right. And you know what? My hearing today was not what it was when I was 18 years old. And that's because too often I was experiencing sounds that could hurt my ears because of the intensity. I wish I would have listened then. But anyway, let's keep moving on. Let's go to the decibel level of all of these sounds. Okay? The decibel level. Now, we have a formula to find the decibel level of a sound based upon its intensity. It's a simple formula. The decibel level of any sound is 10 times the common log of the intensity of the sound over I sub 0. So, and remember, The intensity of a barely audible sound is just I sub 0. So let's substitute. Intensity is barely audible. That's just I sub 0. So what is 10 times the common log of I sub 0 over I sub 0? Well, that would be 10 times the common log of 1. And if you go to your definitional logarithm, that's 10 to the what power equals 1. That would be a 0. So 10 times 0 is 0. So the decibel level of a barely audible sound, that first sound you can hear, is 0. Now, let's keep doing this, okay? So what is the decibel level of a whisper? Well, that's going to be 10 times the common log of the intensity, which is 10 times I sub 0 over I sub 0. See how I wrote that? All I'm doing is replacing this numerator every time with the intensity of that sound. And now let's simplify this. Now here, the I sub 0's cancel, and I have 10 times the common log of 10. So I have to think, what is the common log of 10? Well, what is the log base 10 of 10? That'd be 10 to the what power is 10, and that's just 1. 1 times 10 is 10. And now I hope you see the pattern, okay? The decibel level of a barely audible sound is 0. 10 to the 0 times I sub 0. The decibel level is 0. All right? The decibel level of a whisper is 10. And look at this. The intensity is 10 times I sub 0. Okay? Now, what is the decibel level of the sound of leaves in the breeze? Well, let's use our formula one more time. Notice how I put the intensity of that sound right here in my numerator. 10 squared times I sub 0, which I wrote 100 times I sub 0 here. And my I sub 0's cancel, so I'm thinking 10 to the what power is 100. That'd be 2 10 squared. So this is all 2 times 10. That's a 20. And now I definitely see the pattern. All right. 0, 0, 1, 10, 2, 20. I'll bet you the decibel level of soft recorded music is going to be 40. The decibel level of a 2-person conversation is going to be 60. The decibel level of a loud stereo is going to be 80. The decibel level of the sound of a subway train is going to be 100. The decibel level of a jet at takeoff is going to be 120 decibels. And the decibel level when I start to feel it in my ear, that's 130 decibels. You get to that point where you're listening to sounds at a decibel level of 130, believe me, you are damaging your hearing. Okay? So that's the point where, people like when I was a teenager, The Who and groups like Pink Floyd used to get into a little bit of trouble because at their concerts, the decibel level would get to 130 and beyond. Okay? They were damaging people's ears. Now, they weren't scientists, they weren't mathematicians. They didn't realize they were playing at that decibel level. But, again, they got into a little trouble when they realized that was happening. Okay, so keep that in mind. Now, if the intensity of a sound is doubled, what happens to the decibel level? So, this reminds me when I first moved to the University of Portland. I had what I thought was a great Sony stereo system. And most people think that if the intensity of a sound is doubled, what happens to the decibel level? Most people think that the decibel level also doubles, but that's not true. This is false. And let me explain why. Remember, the decibel level of a sound is going to be what? 10 times the common log of the intensity of the sound over I sub 0. So we can use this formula to figure out this question. So here's our problem right here. And again, back to the day I moved into my dorm room, room 121, Shipstead Hall, University of Portland. 2 loud stereos are playing the same music simultaneously. So when I moved into my dorm room, I had this stereo system. It was a Sony stereo system, and I was really proud of that stereo system. It was incredible. All right? And then I met my roommate for the first time. And my roommate, he came from a big money household, and his stereo system, well, it made my stereo system look a little cheap. I was kind of a little upset about the situation. But anyway, my roommate's name was Bob. And Bob and I would turn our stereos on at the same level all the time. We used to get in trouble from the RAs for this. Anyway, if my stereo system is playing at 80 decibels, and Bob's really nice stereo system is also playing at 80 decibels, okay, what is that combined decibel level? Guess what? What is 80 decibels plus another stereo playing simultaneously at 80 decibels? And I have news for you. That is not 160 decibels. It's double the intensity, not double the decibels. So thank goodness for that, because again, my hearing would be way worse if that were the case. All right, but I want to know what is 80 decibels and then another stereo at the same time playing at 80 decibels. What is that decibel level? And here's how it works. It's double the intensity. So what is 2 times the intensity of an 80 decibel sound? That's going to be 2 times, and if you don't remember this part, you can always go back to our table here. And where is it right here? Double the intensity, 10 to the 8th times I to I sub 0. So let's get back to where we were now. Two times 10 to the 8th, remember? 10 to the 8th times I sub 0. There it is right there. So, what is the decibel level of the combined sound? It is, okay, decibel level. How do we find that? Let's use our formula. Decibel level of a sound is 10 times the common log of the intensity of the sound over I sub 0. And we have our intensity of these 2 stereos right here, playing at 80 decibels each. So that's going to be 10 times the common log of 2 times 10 to the 8th times I sub 0 over I sub 0. And now the I sub 0's cancel out. So we're going to get 10 times the common log of 2 times 10 to the 8th power. And now we just punch that out on our calculator. So I'm going to punch this out with you. Make sure you know where that common log button is. And this should be slightly more than 80 decibels, but not that much more. We're not going to hurt our ears. So 10 times the common log of 2 times 10 to the 8th power. And I'm going to put that 2 times 10 to the 8th in parentheses, just the way I see it. And I'm getting a little bit more than 83 decibels. Okay? So again, if my stereo is playing at 80 decibels and Bob's stereo is playing at 80 decibels at the same time, then the decibel level of the sound that we hear in our dorm room would be approximately 83 decibels. So By how many decibels is the decibel level of the two stereos greater than the decibel level of one stereo? Well, we just increased that decibel level by 3 decibels. All right, isn't that cool? Okay, I miss my old roommate Bob. You know, that was in the early 80s, and I just talked to Bob yesterday. He's doing great. His brother just turned 60 years old, and they had a big old get-together, all of his brothers. They met on Mount Hood. I think it was not Timberline Lodge, it was Mountain Hood Meadows, and they were skiing yesterday, having a ball. Okay, now, let's get to this little statement right here, and make sure you know what's on the other side of our if and only if. So, the log base b, any base of x equals a, if and only if, and you got to go back every time you see this, think about your definition of a logarithm. That's going to be, what's my base? B to the a power has to equal x. And this is how we go from a logarithmic equation to an exponential equation. We just used our definition of a logarithm, and this works for any base. Okay, so how do we use this now? You're going to have several problems that you can do right in your head if you understand this definition. So the log base 5 of 25, what does that equal? So you should be thinking 5 to the what power is 25? And 5 to the what is 25? Okay, well, let me see. Isn't 5 squared 25? Guess what? The log base 5 of 25 equals 2, because 5 to the second power is 25. And all we're using is this statement up here. So let's practice a little more. So then what is the log base 5 of 125? And you're thinking to yourself, 5 to the what would give me 125? 5 to the what power is 125? Wouldn't that be 5 to the third? Why, yes. Let's do one more. Hey, let's get a negative answer right here. The log base 2 of 1 over 8. Well, I'm thinking of this like this. 2 to the what power is 1 over 8? And I might even use now common basis. Isn't 1 over 8 2 to the negative 3? So 2 to the what power is 1 over 8 is the same thing as 2 to the what power is 2 to the negative 3. So that has to be negative 3. Oh man, this is great. Okay, so base b exponential function. Okay, that would be f of x equals b to the x, a base b exponential function. Okay, what does that look like? And again, I had this graph available, a quadrant 1 graph. I don't know that I'm going to use the hash marks. I just want the general shape. Okay, and first I need, what's my y-intercept here? Well, that's 1 times b to the x. So that means the y-intercept of a base b exponential function would be 1. Well, I could use this hash mark. Yeah, I did. But now I'm just going to do my general exponential growth. Let's picture b as greater than 1. What would that look like? 0, 1. And if b is greater than 1, I'm going to have exponential growth. So you guys know what exponential growth looks like. It's going to go through my y-intercept and just show that general exponential growth curve. Just like that. So there's my rough sketch of f of x equals b to the x power. Now, we're going to use that to do a graph of a base b logarithmic function. So what's the domain of this function though? F of x equals b to the x. Well, do you agree that I'm going forever to the left and forever very slowly to the right? So the domain is all real numbers. What's the range of that function? Well, If I kept going left, I'd get closer and closer to the x-axis, but never quite get there. So the range is actually my positive real numbers. And now let's use this to get our base b logarithmic function. Okay, now, well, logarithmic functions and exponential functions are inverses of each other. They undo each other when they have the same base. So I'm going to take that line y equals x, and I'm going to use that to graph f inverse of x, which would be the log base b of x. Do you get it? F of x equals b to the x. The inverse of that would be f inverse of x equals the log base b of x. So there's my y equals x. And now, if we do inverse functions, we just take a key point and we interchange the coordinates. So see the y-intercept 0, 1. I already know the x-intercept then of the log base b of x would be this point right here, which is x equals 1 and y equals 0. And now I'm just going to reflect this curve over the line y equals x, and I have the inverse of that curve, and there it is right there. So f inverse of x is the log base b of x. These are inverses. They undo each other. F of x equals b to the x. Exponential growth with a y-intercept of 1. F inverse of x, the inverse of that, equals the log base b of x. That's going to be this log base b function that goes through the x-intercept of 1, 0 and has this shape. Beautiful. So let's talk domain of our blue function right here. Well, the domain of this function, now picture what it's doing. It's going down forever, but never quite reaching the y-axis. So the domain is actually the positive reals. Note, the function f of x equals b to the x has a domain of the set of real numbers and a range of the set of positive real numbers. The domain of its inverse is the set of positive real numbers, and the range, well, I already know that has to be the set of real numbers. And I can see that in this graph too. It goes down forever, and it works up forever, very, very slowly. But my range is the set of all real numbers. Okay, let's go back to that and make sure you guys have all of that information. This is so cool. Okay, so now let's talk about the natural logarithm function, which is a base e logarithm. And we don't write that log base e. We could, but we have a special notation for the natural logarithmic function, and that is ln of x. A log base e, you will always write the natural log of x. Okay, and now let's go back to our definition of logarithm again. Okay, so the natural log of x, that's a log base e, equals k. That means to go to an exponential function, what's my base here? It is e. E to the k power has to equal x. There you go. And that is your definition of log. We use that all the time. Okay, so let's use this to solve questions like this. All right, find the value of x to the nearest hundredth. Now, when we solved exponentials before, we got common bases. But how can I write 75 as a base 10 number? That's going to be tough. So I have to have another way to do that. And what I do is, what undoes exponential function? A logarithmic function. And guess what? I could do the log base 10 of both sides right here, but most people just like to use natural logs. So guess what? I'm going to take this exponential function and I'm going to do the natural log of both sides to solve for that x. So I'm going to go the natural log of 10 to the x equals the natural log of 75. Now, again, they are going to expect you guys to start using your laws of logarithms now, all right? And you guys have seen this before, okay? Last year, you knew that if you had a logarithm, the natural log of 10 to the x, what can you do with this x? Some of you will remember you can bring that out front as a coefficient. Laws of logarithms, and I'm going to give them all to you today, even though they're expecting that you have seen these before and they're going to want you to use them today in your homework. I'm going to give them to you to make sure, because I know last spring, we were in remote learning. So let's take this exponent, and I can do this anytime I have a log any base to a number to a certain power. I can bring this out front. So that means if I did bring this out front, so this is now x times the natural log of 10 to the x, and I brought the exponent out front, then to solve for that x, I'm just going to divide both sides by the natural log of 10. So that x has to equal the natural log of 75 divided by the natural log of 10. There it is right there. So to approximate that x, I just punch that out. And I'm going to go ahead and do that right now in my calculator. Please do this with me. So I'm going to go the natural log, and that button is right underneath the common log on your calculator. The natural log of 75 divided by the natural log of 10. And what does that equal? That is approximately 1.875. Let's see what I rounded that to. 1.88. There you go. By the way, you could have also done the common log of both sides. So what if I punched out the common log of 75 over the common log of 10? Try that. Guess what's going to happen? The common log of 75 divided by the common log of 10. And guess what I'm going to get? The same thing, 1.875061263. So again, most people, when you're solving an exponential equation, like we started with right there, all you do is simply take the natural log of both sides. Just like that. And then you use laws of logarithms to bring this exponent out front as a coefficient. And then you're left with x times the natural log of 10 equals the natural log of 75, and you divide both sides by that natural log of 10. And then just punch that out. 1.88. Okay? Now the same thing over here on this one. E to the x equals 75. Now when I take the natural log of both sides, what is the natural log of e to the x? Well, those are direct inverses of each other. They undo each other. So if I have the natural log of e to the x, that's going to leave me x. And on the right, I still have that natural log of 75. Because these canceled over here, I'm left with x. So let's punch that out. X equals the natural log of 75, and that is approximately 4.317488114. What did I round that to? Probably to 2 decimal places, because I usually try to be consistent. So I'll bet you that's going to be 4.32. There it is, 4.32. And that is how we solve exponential equations where we cannot get common bases on both sides. We just take the natural log of both sides. Okay, now the homework is 5.5, 1 through 24. And in some of the problems right at the end, 19 through 22, you cannot do those without the laws of logarithms. And you saw those last year, but I'm going to give you a little help on those. Here they are right here. So I would print these out and make sure you understand these. And we're going to get into these very heavily in our next lesson. And you're going to experience a little bit of these in some of your homework today. So let's go back and make sure you have that homework written down. Okay. And then make sure you have your laws of logarithms, so you can do some of those tougher problems. And if you have these laws of logarithms down, those tougher problems are actually quite easy. You guys have a great day, and give me an email if you have some questions. Thanks so much. Oh, look what I did too. I even threw the laws of exponents onto this, so you have everything you need right here. Look at this. The laws of exponents, the laws of logarithms. If I threw your trig identities on this sheet, you'd have everything you need for calculus right there. Don't worry, I won't throw that all at you at one day. Okay, have a good one.